How does a lifeless electron know that someone is watching it? This is not a scene from science fiction. This is a real mystery uncovered by scientific experiments, one that even the best scientists still cannot fully explain. Imagine firing thousands of bullets at a metal plate with two narrow slits. Most of them hit the plate, but a few pass through the slits and form two clear lines on the wall directly behind them. Now replace the bullets with electrons. This time, instead of two lines, you get a series of scattered bands. Strange, right? And if that is not strange enough, place a detector near the slits to check which path each electron takes. Suddenly, the pattern changes. Two lines appear, just like you would expect if they were bullets. It is as if the electrons knew they were being watched and changed their behavior accordingly. But how? How can the simple act of observation alter the behavior of matter itself? The natural explanation is that the detector is somehow disturbing the electrons. But the experiments that followed shattered this idea, and with it, many of our assumptions about reality. Some of these experiments even suggest something more unsettling, that the future may be influencing the past. And the final experiment in this video might just leave you speechless. It is results like these that make the quantum world not just strange, but deeply mysterious. Even Albert Einstein found it hard to accept. He once called these effects spooky. This video will take you through some of the most mind-bending experiments ever done in science. There are no complicated theories or formulas used here. Just clear and simple explanations of some of the weirdest experiments, showing why the world of small particles behaves in ways completely unlike anything we experience in everyday life. And by the end, you might begin to question what reality truly is. And since our modern world already runs on technologies powered by these very principles, maybe it is time we start understanding them, not just as theory, but as a glimpse into reality itself. Hi friends, welcome to a new video from Science Simplified for All. If we look at history, many of the problems related to small particles began with the study of light. Throughout different periods, several scientists and thinkers tried to answer one simple question: what exactly is light? One of the earliest detailed explanations came in the 1670s from Sir Isaac Newton. According to his corpuscular theory, light is a stream of tiny particles. Using this idea, Newton was able to explain phenomena like reflection and refraction. He also made important contributions to the study of colors in light. Around the same time, a Dutch scientist named Christian Huygens proposed a very different idea. He believed that light was not made of particles, but of waves. Using this wave theory, he too was able to explain reflection and refraction. However, during that period, Newton's fame and influence was so strong that Huygens's wave theory did not gain much attention. It was only later that things began to change. In 1801, a scientist named Thomas Young performed an experiment that changed everything. It is called the Double Slit Experiment, and today it is considered one of the most puzzling experiments in the history of physics. In fact, many of the mysteries of quantum mechanics are rooted in this very experiment. This is actually an experiment you can try at home. Take a piece of plastic or any material that does not let light pass through. Make two narrow slits very close to each other. Then shine a laser light so that it hits both slits evenly. Even a small toy store laser will do. Most of the light from the laser will be blocked by the plastic, but the portion that passes through the two slits will fall on the wall or screen behind it. Now here is the twist. What you see on the screen is not just two bright lines behind the slits. Instead, you get a pattern of many lines. That is the strange part of the double slit experiment. Thomas Young's original experiment in 1801 was slightly different from this. Since lasers did not exist back then, he used other methods to produce coherent light that behaves in a similar way to laser light. The materials he used were also different, but the basic idea remained the same. When he directed the light through two narrow slits, he too observed the same pattern of alternating bright and dark bands. This pattern is called the interference pattern. This interference pattern has some unique features. At the exact center, there is a bright line. On both sides of it, there are two dark lines where no light falls, and beyond that, two more bright lines. The pattern continues in this alternating sequence of bright and dark bands. The central bright line is the most intense, and the brightness of the other bright lines gradually decreases as you move outward from the center. The real question here is, how does light, passing only through two slits, create so many lines like this? If light were just a stream of particles, this should not happen. Just like in the case of bullets, we would expect only two lines directly behind the slits. But if light behaves like a wave, then a pattern like this becomes possible. To understand how this pattern forms, let us take an example we are familiar with: waves on the surface of water. Imagine a tank filled with still water. Now, suppose we drop a stone on one side of the tank. Waves begin to form at the point where the stone falls and start moving toward the other side. Now imagine placing a plate with two slits in the path of these waves. Most of the wave gets blocked, but a portion of it passes through the two slits. What happens next is interesting. From each slit, a new wave front emerges, as if the slits have become two new sources of waves. As these two wave fronts move forward, they begin to overlap. In some places, the peak of one wave adds to the peak of the other wave, and the trough of one wave adds to the trough of the other. This is called constructive interference. That is what happens here. The high points are marked with a yellow dotted line, and the low points are marked with a blue dotted line. Along this line, the high points of the two waves combine at these positions, and in between, the low points of the two waves also combine at these points. The result is a wave with higher peaks and deeper troughs, a stronger wave. This is called constructive interference. But waves can combine in another way too. If the peak of one wave meets the trough of another, they cancel each other out. This is called destructive interference. That is what is happening along this line. The high part of one wave and the low part of the other meet and cancel, creating a region where there is no wave at all. So, in the image shown here, you can see alternating lines, some where the waves have added up, creating larger waves, and others where they have cancelled out, creating regions with no waves. And when these waves hit the back wall, they produce alternating regions, some where larger waves strike, and others where no waves reach at all. This is exactly what happens in the case of light as well. The light waves that emerge from a light source travel forward and hit the barrier. Most of the light is blocked, but the portion that passes through the two slits moves ahead as two new wave fronts. When these two wave fronts meet, interference occurs, just like we saw earlier. Lines of constructive interference and destructive interference are formed alternately. When these interference lines hit the back wall, the regions where constructive interference occurs appear as bright lines, and the regions with destructive interference appear as dark lines, areas where no light reaches. This is what creates the interference pattern we saw earlier. To summarize, the fact that we get an interference pattern when performing the double slit experiment is one of the strongest proofs that light behaves like a wave, and that is exactly what Thomas Young's experiment demonstrated back in 1801. It showed for the first time that light is a wave. Later, by the 1860s, James Clerk Maxwell showed that light is not just a wave, but an electromagnetic wave. And so, for nearly 100 years, the idea that light is a wave remained firmly accepted. By the early 1900s, scientists began noticing that the wave theory of light could not explain certain phenomena. In effects like blackbody radiation and the photoelectric effect, light did not behave like waves at all. To explain blackbody radiation, a scientist named Max Planck introduced a new idea in 1901, the concept of the quantum. This marked the beginning of a new branch of science known as quantum physics. Later, in 1905, Albert Einstein proposed that light is not a continuous stream of energy, but rather a stream of discrete packets of energy called photons. Using this idea, he was able to accurately explain the photoelectric effect. For this contribution, Einstein was awarded the Nobel Prize. But this raised a contradiction. The double slit experiment had already shown that light behaves like a wave. And now, Einstein's work suggested that light is also a particle. This is how the idea of dual nature emerged, the conclusion that light exhibits both wave and particle properties at the same time. This became known as wave-particle duality. As we go forward, things only become stranger. In 1924, a scientist named Louis de Broglie proposed that just like light has a dual nature, matter particles might also have wave-like properties. It is easy to accept that light, which is energy, can behave both like a wave and a particle. But electrons and protons are real matter particles. So how could they possibly have wave nature? To test this, the Davison-Germer experiment was conducted in 1927, and it showed that electrons do indeed have wave-like properties. However, a true double-slit experiment using electrons, similar to what Thomas Young had done with light, was not performed until 1961. Just like with light, a beam of electrons from an electron source was directed toward a plate with two slits. Most of the electrons hit the plate and got blocked, but some passed through the slits and reached a photographic plate placed behind it. Since electrons are particles, they were expected to fall in two straight lines directly behind the slits. But after the experiment, when the photographic plate was developed, what they found was a clear interference pattern. This became even stronger confirmation that electrons also exhibit wave-like behavior. But we still know that electrons are real physical particles. For interference to occur, there must be at least two wave fronts. That means, at any given time, there should be two electrons passing through the plate, one through each slit, to cause interference. So, what happens if we release the electrons one by one toward the plate? In this case, after releasing one electron, we wait for a short while before releasing the next. In this way, we ensure that at any given instant, only one electron is passing through the slits. Since one electron can pass through only one slit at a time, there will be only one wave front coming out at that moment. There is no other wave front present at the same time coming from the other slit for it to interfere with. Naturally, no interference should happen, and each electron should hit the screen directly behind the slit it passed through. So if we keep on releasing electrons one at a time for a longer duration and later develop the photographic plate, we should expect to see two lines, matching the positions of the two slits. There should be no possibility of getting an interference pattern. Testing this logic was the next goal of scientists. The experiment was called the single-particle double slit experiment. Once the setup was ready, electrons were released one by one toward the plate. Some of them were blocked by the plate, and a few passed through one of the slits and hit the photographic plate. No matter what, they ensured that only one electron passed through the slits at a time. After repeating this for a long time and developing the photographic plate, the result was again an interference pattern, not just two lines. But how is that possible? A single electron can pass through only one slit at a time. So, what exactly is it interfering with? Now comes the obvious question. Could a single electron be passing through both slits at the same time? According to our normal logic, that should be impossible. But to find out, scientists tried the next step. They decided to place a sensor or detector right next to the slits to find out which slit the electron was actually passing through. This setup is called the which-way experiment, and it was first conducted in the 1980s. As usual, the experiment was set up, and electrons were released one by one toward the plate. This time, the detector recorded which slit each electron passed through. After running the experiment for a while, they developed the photographic plate. But this time, there was no interference pattern. Instead, they saw just two lines. That means, when we try to find out which slit the electron passed through, the electrons stop behaving like waves and start behaving like proper particles. This is what is known as the observer effect. It explains why particles behave differently when observed and when not observed. The same experiment has been repeated many times, changing the position and type of detector, but the result was always the same. Just as we all tend to believe, scientists also concluded that the detector used to observe the electrons must be disturbing them in some way. So the next step was to find a method to detect which slit the electron passed through, without disturbing the electron at all. That is when they realized they could use a phenomenon called quantum entanglement. Entanglement is a phenomenon in which certain properties of two particles become linked with each other. When that happens, measuring the state of one particle allows us to know the state of the other. In a way, you could even think of them as twins. Such particles are called an entangled pair, and the phenomenon is known as quantum entanglement. Entanglement can occur not only in physical particles like electrons, but also in photons, the particles of light. Scientists decided to use this special feature of particles to determine which slit a particle passed through in the double slit experiment. This time, instead of electrons, they used photons, particles of light. The setup of the experiment is as follows. Photons are emitted one by one from a light source toward the plate. Some of them are blocked by the plate, while others pass through one of the two slits and move forward. Just behind the slits, there is a special type of crystal. The unique property of this crystal is that every photon that passes through it gets split into two identical photons. These two photons are entangled, so if we measure one of them, we can infer the state of the other. Now, suppose a photon passes through the first slit. As it reaches the crystal, it splits into two entangled photons. One of them goes and hits the screen. The other reflects off a mirror and reaches detector A. Now, suppose a photon passes through the second slit. It too is split into two entangled photons by the crystal. One of them goes to the screen, and the other reflects off a mirror and reaches detector B. The photon that hits the screen is called the signal photon, and the one that goes to a detector is called the idler photon. The key point here is that we are not measuring the signal photon, so we are not disturbing its path in any way. What we are measuring is the idler photon, its entangled partner. By checking whether the idler photon reached detector A or B, we can determine which slit the original photon passed through. That is the goal of this experiment. By this time, photographic plates had been replaced with detector screens. The computer records exactly where each signal photon hits the screen, and also which detector its corresponding idler photon reaches. There is also a system called coincidence counting, which helps to match each signal photon with its entangled idler partner. Using this setup, photons were released continuously over a long period. The computer kept recording where each signal photon landed on the screen and which detector its corresponding idler photon reached. But when the results were analyzed, there was no interference pattern. Again, even though we were only measuring the idler photon, the signal photon seemed to know that. In other words, the signal photon was still being affected. Now comes a critical variation in this experiment. The detectors that measure the idler photon are placed much farther behind the screen. That means the idler photon is detected only after the signal photon has already hit the screen. So, by the time the signal photon lands on the screen, it has no way of knowing whether its entangled partner will be measured or not. This setup is called a delayed choice. According to this logic, measuring the idler photon should not affect the signal photon in any way. Therefore, this time, we should definitely get an interference pattern. But even in this experiment, no interference pattern was observed. What should we make of that? It is confirmed that the signal photon hits the screen first. Only after that does the idler photon reach the detector. It can be interpreted in a way which means something that happens to the idler photon in the future is influencing something that has already happened to the signal photon in the past. In other words, we might infer from this that the future can affect the past. This idea is known as retrocausality. However, many scientists now believe that this one experiment cannot be taken as proof of retrocausality. There are even a few debunking videos that argue this experiment does not prove retrocausality. So, let us rule out the possibility of retrocausality for now. But there are two things everyone agrees on. One, even if the detector does not disturb the signal photon in any way, it is still being affected. Two, the connection between entangled particles goes beyond the separation of distance and time. No matter how far apart the two particles are, or whether they exist at different points in time, one ahead and one behind, measuring one instantly affects the other. Nobody disagrees with that. Is that not weird enough? Well, the questions do not end here either. To truly complete the title, the experiment that shocked the world, there is one more experiment we need to explore. It is called the quantum eraser experiment, or more precisely, the delayed choice quantum eraser experiment. The experimental setup for this one is a bit more complicated, so you may want to pay closer attention or even take a short break and come back to it. The basic setup is similar to what we saw earlier, but this time these two mirrors are partially silvered mirrors. That means when photons hit them, about half of the photons are reflected, and only those will go on to reach detectors A and B. The remaining photons pass straight through the mirror. Whether a photon is reflected or passes through is completely random. Now, to detect the photons that pass through, two more detectors are used. Let us call them detector C and detector D. The paths that lead to detector C and D also include more partial mirrors. These are arranged in a special way. The arrangement is a bit complex, and we do not need to go into the full details here. But the idea is simple. The photons passing through the first set of mirrors have a chance to mix before reaching C or D. Because of this mixing, we cannot tell which slit the photons hitting C or D originally came from. That is, if a photon is detected at A, we can say it came from the first slit. And if it is detected at B, we know it came from the second slit. But for the photons that reach detectors C and D, we lose the information about which slit they passed through. That is because photons from both slits can end up at both detectors. In short, this additional setup erases the which-way information. That is why this part of the setup is called the eraser circuit. And because this circuit is included, the experiment is called the quantum eraser experiment. Now let us see how this experiment actually works. As usual, photons are released one by one from the photon source toward the plate. Some of them are blocked by the plate, while others pass through one of the two slits. Let us say a photon passes through the first slit. When it reaches the crystal, it splits into two photons. One of them, the signal photon, goes to the screen and gets recorded there. The idler photon now has three possibilities. 1. It may reflect off the first mirror and reach detector A. In that case, it is recorded that the original photon came through the first slit. But if it does not reflect and instead passes through the mirror, it can end up at either detector C or D. Both outcomes are equally likely. Now suppose another photon passes through the second slit. It also passes through the crystal and splits into two. Its signal photon lands on the screen. The idler photon again has three possibilities. 1. It may reflect off the second mirror and reach detector B. In that case, it is recorded that the original photon came through the second slit. If it passes through the mirror without reflecting, it can again reach either detector C or D with equal probability. So, whenever a photon is detected at A, we can be certain it came from the first slit. Whenever one is detected at B, it came from the second slit. But if it is detected at C or D, we cannot tell which slit it came from, because photons from both slits can end up at both of these detectors. The position and time at which each signal photon lands on the screen are recorded by the computer. Similarly, the time at which the idler photon reaches any of the detectors is also recorded. So, if an idler photon hits any of the detectors, we can use this data to find out where its corresponding signal photon landed on the screen at that same moment using coincidence counting system. Over time, as the experiment continues, photons will land at detectors A, B, C, and D, and at the same time, their corresponding signal photons will be recorded on the screen as well. Now comes the real twist. Whenever the idler photon is detected at detector A and we look at where its corresponding signal photon landed on the screen, we do not get an interference pattern. That is because we have the information that the photon detected at A came through the first slit. Similarly, whenever the idler photon is detected at detector B, and we check where the corresponding signal photon landed, we still do not get an interference pattern. Again, this is because we know it came through the second slit. But whenever the idler photon is detected at detector C or D, and we look at where the corresponding signal photon landed on the screen, we get a clear interference pattern. This is because detectors C and D do not give us any which-way information. We cannot tell from them which slit the photon came through. In short, when the which-way information is available, we do not get an interference pattern. But when that information is erased or unavailable, the interference pattern reappears. So, it is not the act of detecting which slit the photon came through that destroys the interference. It is the fact that the information remains available. Put simply, when we know which slit the photon went through, it behaves like a particle, and we do not get an interference pattern. But when we do not know which path it took, the photon behaves like a wave, and the interference pattern reappears. This is the most extreme form of what we have seen so far. Particles showing completely different behavior depending on whether or not they are being observed. The word observed here technically means being measured or detected. In quantum mechanics, it is said that measurement causes the wave function to collapse. But the truth is, nobody really knows why the wave function collapses. Or in other words, nobody truly understands why quantum particles behave differently when they are observed. Even in the case of quantum entanglement, no one knows what strange connection exists between two entangled particles. A connection that seems to go beyond both distance and time. It is the strange and illogical phenomena like these that make quantum mechanics feel so mysterious. Even though these experimental results seem bizarre to us, scientists like Niels Bohr and Werner Heisenberg, who laid the foundations of quantum mechanics, had already anticipated that things would behave this way. Many of these experiments were conducted only after they had passed away. Yet, the results turned out exactly as they had predicted. It was this very aspect of quantum mechanics that led to deep disagreements between them and Einstein. However, when it comes to quantum mechanics, history has shown that Einstein was wrong, and Bohr and Heisenberg were right. Quantum mechanics is still weird, but since modern life runs on technologies built from it, maybe it is time we start understanding it, not just as theory, but as a glimpse into reality itself. If you like this video, please give it a like and share it with others. For more videos like this, make sure to subscribe to the channel and enable the bell icon. Thank you.